Professor R. Ashokamani, former professor and head of the Department of Physics, Anna University, Chennai, and presently guiding 5 research scholars. He has more than 40 years of UG and PG teaching experience and 25 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics which has an international publication. He has participated in several international conferences both in India and abroad. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we are going through the paper on physics of materials intended for the semester 3 of the electronic students, and we are seeing the section on bondings in solids. In the previous lecture we had the covalent bonding and the importance of covalent bonding. In this lecture 4 we will go through the theory of covalent bonding. Now, for students of electronics, as I told you in the earlier lecture, covalent bonding is of great significance, because in all semiconducting materials, either you take silicon or germanium or the optoelectronic material like gallium arsenide, it is a 3,5 compound semiconductor, or you take a 2,6 semiconductor like indium telluride or indium phosphide, or the ternary systems like AgGaS2, they are called the ternary chalcopyrite, or the ternary pnictides, which are used for solar cell applications. In all these systems, the bonding that prevails is the covalent bonding. So, the covalent bonding should be properly understood. How the electrons behave in a covalently bonded solid should be properly understood by especially the electronic students and the electrical engineering students and the computer science students who are working with semiconducting materials. Now, that is the reason why I go deep into the theory of covalent bonding. Now, the theory was proposed by Heitler and London in 1927, and the contents of today's lecture are: first we will discuss the Pauli principle, the Hamiltonian of the hydrogen molecule. One of the lectures I told you the simplest system that you can think of for covalent bonding is the hydrogen molecule. When you combine 2 hydrogen atoms, you get a hydrogen molecule. The bonding in hydrogen molecule is fully covalent. So, that is a starting point. Therefore, to understand the covalent bonding, instead of silicon or germanium, we will start with the elementary system like hydrogen molecule. Each hydrogen atom got only 1 electron, and you combine, you get the hydrogen molecule. Then from that determine the energy versus distance curve that can be generated. Then you have to comment about the spins of the electrons of the hydrogen molecule. How many electrons are there in the hydrogen molecule? There are 2. What about the spin states? Now, these are the things that we will be discussing in today's lecture. And the electrons are quantum mechanical objects. They are to be what is called the Pauli principle. You would have studied even in high school the Pauli principle, which says that no two electrons can have the same set of quantum numbers. If you remember, you do not write the same quantum numbers, that is what you will be knowing by now, but I am going to give a quantum mechanical treatment of the Pauli principle. It is not stated in terms of the quantum numbers n, l, ml, ms. You would have studied in high school. That is a preliminary thing that based on the vector atom model, where we treat the electron as a particle, right. But I told you in the last lecture itself, your hydrogen atom has one electron, but you do not consider the electron as a particle. You have the charge distribution. I showed a nice animation where the charge clouds of the two hydrogen atoms, they come and join together, and they form the hydrogen molecule and so on. You talk of sharing of electrons. I mean, in the elementary level, that term sharing is not very good. So, anyway, the point is, you do not consider the electron as a particle. On the other hand, you have a charge cloud. So, the Pauli principle is important, right. When you are discussing about electrons, in all bondings, electrons play the important role. The bonding is due to electrons, right. Now, the electrons are not classical objects like cricket balls and so on. So, the Newtonian dynamics cannot be used. So, you have to use the quantum mechanical concepts, and so the Pauli principle, as all of you know, should be used when you are dealing with a system of electrons, 2 electrons or 3 electrons, or say n number of electrons. Now, let us consider the Pauli principle for a n electron system. N electron system means you may have an atom where there may be n may be 14, as in the case of silicon, right. It may be some other number. So, n is some number. So, you got 14 electrons or 5 electrons, whatever be the thing. Now, you have this is the Pauli principle. It can be stated in a quantum mechanical language. You have PRS operating on the wave function psi, R1, R2, then R S, then Rn. Rn is the nth electron. Then what is R1? R1 refers to x1, y1, z1, the space coordinates, and the spin state, right. You know, the electrons have got a spin, intrinsic angular momentum, the spin angular momentum, and so apart from the space coordinates x1, y1, z1, I should specify the spin state also. Similarly, R2 refers to or stands for x2, y2, z2, that is space coordinates, then the spin state. Supposing R1 may be like this, spin up, and R2 may be spin down, or R2 may be spin up, and so R1, R2, or R suffix R and R suffix S, and then Rn, they refer to the space coordinates and the spin state of the electron 1, 2, R, S and N. You got N electrons, right. So, what is PRS? PRS refers to the interchange operator or the exchange operator. What you do is you interchange the 2 electrons, right. You got electron here, that is RR refers to XR, YR, ZR, the space coordinates, and the spin state may be up. Then you have got PS here, right. I mean RS here, right. This is the S electron. Now, you interchange the 2 electrons, right. You interchange the 2 electrons. When you interchange, you have got a wave function. You write down the wave function like this. You interchange the 2 electrons. You have got orth electron here, S electron here. You interchange the 2 electrons. When you interchange, this operator which interchanges. What is the operator? PRS is the interchange operator or the exchange operator. It exchanges the 2 electrons. The orth electron, the S electron, the 2 electrons are interchanged, right. When you interchange, what do you get? Now RR goes to this RS, right. RS goes to RR goes to RS, right. This is what the operator does. The operator simply interchanges the 2 electrons, right. That the interchange wave function, that the wave function that you have got after the interchange should be minus of the original wave function. The original wave function is here, right. It should be minus of the original wave function. That is the Pauli principle, right. The Pauli principle simply states that the wave function that you have for describing an electron system should be antisymmetric with respect to the space coordinates and the spin state. It means that if only it is antisymmetric, then upon interchange you should be getting the wave function with a negative sign. Then you see the wave function is having the correct antisymmetric character, right. So, R1 R2 they stand for the space coordinates and the spin state of the electrons, or as well as the spin states of the electrons I told you. So, psi will be equal to psi space and psi spin, right. The space part x1 y1 z1 and the spin part, right. So, Pauli principle demands that psi should be antisymmetric. What is antisymmetric means? Upon interchange you have to have the wave function with a negative sign. If it is occurring with a positive sign, then it is a symmetric wave function, but now you have to have antisymmetric thing. That means the change in sign should be there. The change in sign, that upon when the operator operates on the wave function, you should have a negative of the old wave function, that is the change in sign after the exchange operator, right. That should be clearly understood, right. Now, whatever I have written so far, right, in a very simplified way, what you do is this gets much simplified. Suppose I write the wave function for the hydrogen molecule as psi 1 2, where 1 and 2 refer to x1 y1 z1 spin up, 2 refers to the second electron x2 y2 z2 the space coordinate, and spin up or spin down for the second electron. So, what is p12? P12 is the interchange operator. So, now what will happen now? Psi 1 2 has become psi 2 1, right. I am interchanging the electron that I am having here at the space coordinate x1 y1 z1 and x2 y2 z2, it may be spin up and this may be spin down or spin up. I interchange, right. Upon interchange I get what is called psi 2 1. This psi 2 1 should be equal to minus of psi 1 2, right. If that is the simplest way by which you can express the Pauli principle, this is the simplest way. You see the elegance, right, the simplest way of explaining the Pauli principle following, right. The mathematically it shows the correct antisymmetric character, because you got a negative sign here. So, the point is any wave function that describes an electron system, an electron system should be having the correct antisymmetric character. By this what I mean is, upon interchange you should get the wave function back with a negative sign, right. That is the Pauli principle, that is the quantum mechanical way of expressing the Pauli principle. Unlike what you have studied in the school, N, L, M L, M S, they should not have the set of quantum numbers are needed for describing one electron. Then the same set, all the numbers should not be again repeated for the second electron, right. That is what you would have studied in the at a lower level, but this is a quantum mechanical way of describing the thing. The more beautiful way of writing down this the two electron system is as follows, right. You write, you look at the hydrogen molecule, right, because we are talking about hydrogen molecule. You look at the hydrogen molecule now, we have got the protons A and B, right. The protons A and B, you got a proton here, and you have got electron 1 here, electron 2. You know, in the hydrogen molecule you got 2 electrons, right. Okay. And now I can write psi A R1. Psi A R1 means the probability of the electron 1 to be associated with the nucleus A, right. You got a nucleus here, right. Psi A1, now 1 associated with the nucleus A, and similarly same electron 1 can also be associated with the nucleus B. For that I will be writing psi B1 and this is psi A1, and similarly the second electron also belongs to, can be associated with nucleus A and the nucleus B, right. So, this should be clear, both the electrons give rise to the hydrogen molecule, both electrons they partially belong to or associated with the 2 protons. You have got a proton 1 here, proton 2 here, the 2 hydrogen atoms. So, now I will write down, go back to the wave function psi 1 2 will be, I write in the form of, what is it I have done? I have written a determinant on the right hand side of the equation. You have got the equation psi 1 2 is the wave function that describes the 2 electron system. Now, you see the on the right hand side a determinant, right. So, psi a or one. What is psi a or 1? The square of which gives psi a or 1 square gives the probability of the electron 1 to be associated with the nucleus A. Similarly, R 2 refers to the probability of electron 2 to be associated with the nucleus B, and so on. And so, at this point of time we will have a break and then we will resume later. So, welcome back after the break. Now, we are discussing the Pauli principle. Instead of writing down the wave function in the form in which I wrote down earlier, now what I am doing is now I write wave function psi 1 2 in the form of a determinant, right. And what I would like to tell you is this psi a or 1 is a measure of what is psi a or 1? It is the square of which gives the probability of electron 1. You have a 2 electron system, the electron 1 to be associated with the nucleus, the first nucleus A, you have got 2 nuclei, right, A and B. Similarly, psi a or 2, the nucleus A is the same, electron psi a or 2 square, because they are the wave functions, the square of them, the wave functions will give the probability, right. So, psi a or 2 square gives the probability of electron 2 to be associated with nucleus A, right. And similar thing goes for psi b or 1 and psi b or 2, right. Now, this is a beautiful determinant. What is the beauty? Now, this R 1, the first column, can be thought as a quantum state, right. The first column can be thought of as a quantum state. This is another quantum state. Now, what I have been telling you so far, the wave function should be antisymmetric. That means, when you change the 2 electrons, right, you should get back the wave function with a negative sign. You take any determinant, you got a determinant here, you got a column here, you got another column here, right, a 2 by 2 determinant. When you interchange the 2 columns, what will happen? You know, in a determinant, when 2 rows or 2 columns are interchanged, you get back the same determinant with a negative sign, right. That is a elementary thing that you have studied with regard to determinants. When you have got a determinant, when the 2 rows are interchanged, you get the same determinant with a negative sign. You are getting the same determinant with a negative sign, it is equivalent to what I showed you here, that you have the wave function here, you get back the same thing, the same wave function with a negative sign. Instead of writing this wave function in this form or in this form, right, P 1 2 operating psi 1 2 will be equal to psi 2 1, that will be minus of psi 1 2, you got a negative sign. That negative sign comes automatically when you interchange the 2 columns, right, in a 2 by 2 determinant, or it may be nth order determinant for an electron system. The second point is, what is Pauli principle? Tell me what is Pauli principle. What you have studied in a elementary level, no 2 electrons can have the same set of quantum numbers. Now, those quantum numbers ought to be forgotten, right. You are identifying an electron as a particle is no longer true, that is the electron has been replaced by charged cloud, you are talking about a wave function and so on. Now, look at, supposing you make R 1, as I told you, R 1 is a quantum state, right. What is R 1? X 1, Y 1, Z 1 spin up. R 2 may be X 2, Y 2, Z 2, it may be spin up or spin down, right. And supposing you make R 1 equal to R 2, what will happen? You make R 1 is equal to R 2, what will happen to the determinant? The determinant will, what will happen? It will vanish, it will become 0, right. This determinant will vanish when you force R 1 equal to R 2. What is R 1? Or is a quantum? R 1 is a quantum state, R 2 is another quantum state. It is something like N, L, M, L, M, S that you study in the vector atom model. So, no 2 electrons can be found in the same quantum state. R 1 is a quantum state, R 2 is another quantum state. You cannot, you have a quantum state Now, you cannot have the same quantum state 2 electrons. You should not force 2 electrons to go to same quantum state. Now, what is quantum state? Suppose you take 1s electron, you have n, l, m, l, m, s. What are the values? N is 1, 1s state, right? N is 1, L is 0, M L is 0, M S is plus off. This is quantum state. What is the other possibility? Again, you got N is equal to 1, L is 0, M L is 0. M S, if you put plus off, you are violating the Pauli principle, because the two sets of quantum numbers are identical. So, it should be minus off. You cannot have same set of quantum numbers for the 2 electrons. Therefore, now if you make R 1 equal to R 2, that means you are forcing the 2 electrons to go to the same quantum state, or you are trying to have all the 4 quantum numbers to be identical. You cannot have the same quantum numbers repeated for the 2 electrons. That is what you have studied in high school. So, that is elegantly brought out by the determinant. The first one to be remembered is, when you interchange the 2 rows, you get back the wave function with a negative sign, that is a proper antisymmetric character is brought out. The second thing is, when you force 2 electrons to go to the same quantum state, R 1 is quantum state, R 2 is another quantum state, right. R 1 is a quantum state. Now, this electron 1 can be associated with the nucleus A, as I told you just now. Same electron 1 can be associated with the nucleus B also, right. That should be remembered. So, this quantum state R 1, a quantum state R 2, if you force 2 electrons to go to the same quantum state, then such a thing will be, the probability for such a thing will be 0. So, psi 1 2 will vanish when you make R 1 to R 2, that means equivalent to putting same set of quantum numbers, having same set of quantum numbers for 2 electrons, at least one number should be different. So, this is a beautiful determinant which is written by Slater. So, the determinant goes with the name of Slater, the Slater's determinant, right. So, the Pauli principle is very nicely stated by means of the antisymmetric character comes automatically, and again the wave function vanishes when you force the 2 electrons to go to the same quantum state, right. That is the beauty of beauty with which you should look at the determinant, right, in the Pauli principle, right. When note that if R 1 got 2, then the determinant vanishes, which shows that 2 quantum states cannot be identical, or it is impossible to force the 2 electrons to occupy the same quantum state, which is the Pauli principle. Secondly, the antisymmetric nature of the wave function is also brought out, because when you exchange the 2 rows, or the 2 columns that have here, the 2 columns when they are interchanged or exchanged in the determinant, then the wave function gets changed, I mean with a negative sign, you are getting the wave function with a negative sign, right. Remember that the Pauli principle is applicable wherever you have got electrons. So, do not think that the Pauli principle is applicable only to electrons and atoms, that is a wrong concept. Wherever you have got electrons and atoms, molecules, solids, all kinds of solids, whether ionic solid or covalently bonded solid or any other bonding, right. Whenever you have got electrons, that is the spin off particles, the fermions, right, which will be the Fermi-Dirac statistics. Now, the fermions have to necessarily obey the Pauli principle. That should be borne in mind, applicable to atoms, molecules and electrons in solids with all kinds of bondings. This is what I told you with regard to hydrogen molecule earlier. So, you should remember one can be associated with the nucleus A and as well as B, right. That is what I would like to say, psi A or 1, psi A, psi B or 1, that means partial occupation of the quantum state by the 2 electrons, right. Okay, that is what we have learnt with regard to the Pauli principle for a 2 electron system. The 2 columns are interchanged, they are partially occupied. When they interchange, then you get a negative sign, right. Psi A R 1 square refers to the probability of the electron 1 to be associated with the nucleus A, and similar interpretation can be given to the other electron as well, right, other functions as well, right. Psi B or 1 refers to the probability of electron 1 to be associated with the nucleus with the proton B, right. Now, therefore, and now you should remember these things in a very concrete manner. And then we pass on to the Hitler-London theory of the hydrogen molecule. Now, you have in the hydrogen atom only one electron. So, you talk of the 1s wave functions. They are of the form exponential of minus r by a naught. Let me write the wave function as psi a r1 to be equal to e to the power of r a1 by a naught. A naught is the Bohr radius, right. And this is how one writes the wave function, right. Of course, it is not very important to know how the wave functions are written, but the point is you should remember that psi a r1, psi b r1, psi a r2, psi b r2 are the wave function of the electron 1 and electron 2, which can be associated with the nucleus either the proton A or the proton B, right. So, that is what you see. The total wave function system may be written in the form of a determinant, that is what I told you. Now, when you write the 2 by 2 determinant, right, we can when you have a wave function, you write as psi a r1, psi a r2, and the other possibility will be psi a, you have psi a r1, psi b r2, right. You can have psi a r1, psi b r2 plus psi a r2, psi b r1, right. You can have a linear combination psi a r1, psi b r2, then psi a r2, psi b r1, right. You got a plus sign. Here you look at a thing with a negative sign, right. Got a negative sign. So, the 2 electron wave function can be written either this way with a plus sign or with a minus sign. Now, but you have to know which is the correct one, right. Now, this carries immense importance because hydrogen molecule is a problem which has been studied well by Hitler-London to explain the bonding, later by Heisenberg to explain a entirely different phenomenon, namely ferromagnetism. That is an entirely different phenomenon, but I will come to this point later. But now, as far as this problem is concerned, covalent bonding is concerned, the sign is important. The signs plus and minus refer to symmetric and antisymmetric wave functions, and 1 by root 2 comes because it is a normalization factor. But as the Pauli principle is concerned, the wave function should be antisymmetric. So, that means this is antisymmetric, this is a correct wave function because it got a negative sign. So, this is the right wave function that describes the 2 electron system which will obey the Pauli principle. This does not obey the Pauli principle, right. Okay. And the potential energy of the 2 electron system can be written like this. Now, what is that? E square by the Coulomb's law, E square by R A 1, because you have got electron 1 associated with the nucleus A, and the interactions are, you can see the hydrogen molecule, you have got electron 1 to be associated with the nucleus, electron 1 can be associated with the proton A, the same electron 1 to be associated with proton B, and similar thing for the electron 2 also, 2 can be associated with A as well as B, right. Now, therefore, you have got here now E square by R A 1, right, the electron 1 to be interacting with the proton A, right, the first proton. Similarly, you can have second term where you will have the other terms, right, or A 2, that is electron 2 interacting with the same proton A. Now, on the other hand, E square by R B 1 is the E square is the Coulombic law, right, E square by R, right, R B 1 similarly R B 2. So, you got 2 protons and 2 electrons, there are 4 terms, right, the potential energy term. Then comes the interaction between the 2 electrons, the Coulombic repulsion, you got a negative sign, the attractive interaction between the electron and the proton. The last term is the repulsive interaction between the 2 electrons, right. The 2 electron system, you got the potential energy of the electronic system. The last term is the repulsive interaction between the 2 protons. The energy of the molecule is calculated by evaluating the expectation value of the Hamiltonian. The final term of the potential energy is the nuclear repulsion, as I told you just now. The spin factors have not been included. So far, we have not been talking about the spin. So, we write the Hamiltonian in this form, right. How do you write the Hamiltonian? That is, you write minus h bar square by 2 m del 1 square, right, h bar square by 2 m. E is the mass of the electron, del 1 square the kinetic energy operator. This is the kinetic operator for the second electron, this is for the first electron, this is the potential energy, right. And this comes, this last term is the repulsive interaction, or is the distance that separates the two protons, whereas V is the E square by R12. R12 is the two electrons. This is V I showed you the potential energy experienced by the two electrons from the two protons. Now, the last term here refers to potential energy of repulsive energy acting between the two protons, right. That so, this makes the total Hamiltonian. You can calculate the energy E by evaluating the following thing. You write the integral of psi star h psi d tau divided by psi square d tau. This gives the total energy, right. The total energy of the hydrogen molecule, or the expectation value of the hydrogen molecule problem, is obtained by evaluating the right hand side, as I showed you just now. And you find here, this is important expression, you find here 2 E h. What is E h? Is the energy of the hydrogen atom, right. The total energy of the system, it is comprised of the three terms. One is the two separated hydrogen atoms, right. You have got two separated hydrogen atoms, 2 E h, and then comes the second term, that is the, you got the term containing J and K, that should be seen here. The term containing J and K are complicated collection of integrals over the wave function that you find here, J and K, right. And S is what is called the overlap integral. This term J is very important, it is called exchange integral. J is called exchange integral. This term carries lot of significance. Now, what should be the sign of J carries lot of significance, and J is called exchange integral because you are using the exchange operator or the interchange operator. So, the energy of system can be, the whole system can be calculated by this expression. Now, the graph that I show here is the graph drawn between the energy and the interatomic separation or the interproton separation, about which we will see in detail in the next lecture. Now, let me now summarize the lecture that I delivered today. Electrons being microscopic particles, quantum mechanics is to be used to explain all bondings. This I have emphasized very often. Electrons have to obey the Pauli principle, irrespective of you are talking about electrons and atoms, molecules and solids, right. Energy of the molecule can be calculated using the Hamiltonian, as I showed you just now, right. The energy of the molecule can be calculated using the Hamiltonian, that gives the bond length and bond strength. Now, the details regarding bond length and bond strength we have to see in the next lecture. Then we will pass on to the question session. What is the Pauli principle? Whether the above principle should be used only for atoms. The question number 3, how do you find the energy of the hydrogen molecule? With this we come to the end of the lecture 4. In the next lecture we will see the rest of the things. Thank you.